Anybody have any questions before we get going? All right, just a heads up. I think section 2.6, I put the due date for that for tomorrow night. I'm going to post a quiz later this afternoon. That'll be due on Monday, as usual. And I think that's it for the short term here. I have tests for you today, so I'll give those to you at the end of class. So stick around. Remind me if I forget to give those out, but it's time. All right, so section 7, chapter 2 is all about something called related rates. So just to kind of remind you, I mean, we've been doing a lot with derivatives for the last 2 weeks or so. And just remember, we have lots of ways to think about the derivative. We've thought about it as the slope of a tangent line to a function. Thought about it as the slope of the function itself. Also talked about it, being directly related to a rate of change, so the instantaneous rate of change of a function. So that's, we need all of those at different times. Today we're going to be focusing largely on the representation of a derivative as a rate of change. So start with this example here. So I throw a rock into a lake, and where the rock enters the water, a wave is going to emanate out from that splash point. Start simple. What shape is that wave? It's going to be circular, right? I think everyone's probably done something like this. So it's going to be a circular wave. And I want to talk about the rate of change of the radius. So let's unpack a little something here. I'm giving you a description, and you're going to model it mathematically and solve a problem that way. So let's talk about this. I want to describe this quantity, radius. What's a good name for that? R is fine. No need to be clever about it. We'll call it R. That's not equal sign, but R stands for the radius of the wave at any time. And let's come up with a unit here. Based on the way that I've given this to you so far, good units. So as we go, we're going to define all the variables we need. Another variable that's implied in here is, how much time has gone by, time elapsed. And I should measure that in seconds. So let's just go with the units I give you. I'm going to measure some length, radius in meters. I'm going to measure time in seconds. So now I want to describe the rate of change of the radius. So the rate of change I'm giving you here for the radius is 4 meters per second, right? So when you're talking about a rate of change implies, more or less by definition, you have to have two different quantities that are changing together. So in this instance, the radius is growing as what other thing is changing? Time. So the radius is a function of time, basically. So I can even represent this R as R of t for now. Might call it R, might call it R of t, but really it's important to note that radius depends on time somehow. So if R is the radius, or the length of the radius, and t is time, what's a good symbol to use to represent the rate of change of the radius with respect to time? Based on the way that we've been thinking about derivatives so far. What was that? R prime is a good way. What else might we use? What's another one that makes it even more specific what the two quantities are that are changing together? dr dt. I am going to favor, for now at least, dr dt. just because that makes it really clear that as time goes on, the radius is changing somehow. So that variable dr dt is a rate variable. For this situation, what's dr dt equal to? 4. I'll say 4 meters per second, but yeah, 4 is the key there. I did not mean to show that last bullet, but are we okay so far on, we're being really explicit about how we're defining variables, how we're defining rates, but these are going to get a lot more complex pretty quickly, and I think it's a good habit to get into. Any questions so far? All right, now I want to talk about the area. So how fast is the area, like kind of enclosed by that wave? How fast is that area growing after 5 seconds? So I know I'm looking at a circular object. I know something about its radius, but how would I get that? Now I want to talk about area. So how would I relate area to the things I have here with the shape I'm looking at? Yeah, so it's a circular area, right? So I'm going to need this equation right here. And one thing I want to focus on is this. I want to know how fast is the area growing. That implies that I want to look at a rate of change, right? So I have this function here, and maybe I'll even make it more clear that this area function is a function of radius. Maybe you've never written this like this before, but the area of a circle really is a function of its radius. If I want how fast is the area growing after 5 seconds, what do I need to do to this equation here? Find the radius. But I am asking for, maybe it would help if we did this. I want to know how fast is the area growing after 5 seconds. So this is a rate, right? Can I give a name to this rate based on the other like symbols and quantities I have here? I'm looking for the name of a variable. So this is our first one. Maybe I'm. It's not really acceleration because we can think of the dr dt, that's a velocity, right? But I don't need to look at like the rate of change of dr dt. So maybe I'll take over a little bit here. So I want to know how fast the area is growing after 5 seconds. So I'm looking for how fast is the area changing with respect to time. So this right here is the rate of change of area with respect to time. With respect to time. Another variable we should talk about is just A, which is just, what does it just A stand for? Area of wave after t seconds. And how should we measure that thing? Not meters per second. The area is going to be meters squared. If we're talking about the rate of change of that area, then that'll be square meters per second. So now we got a bunch of different variables we're going to look at. Really, there are 3 quantities here. I have the time, I have the radius, and I have the area. But then through differentiation, I can find a couple of other ones. Sebastian, question? often enough that it's worth abbreviating. Okay. So any questions about the variables that we've kind of plucked out of this? How we've defined them, where they came from? All right, then back to this this function here. The area as a function of the radius is equal to pi r squared. I want to find this rate right here, dA dt. If I want to find dA dt, and I have a function of a with respect to r, what do I need to do to start getting closer to finding that dA dt? Go ahead. What is my function for r? Do we agree with that? That r is equal to r of t is equal to 4t? So we're assuming that that ripple is going to kind of grow linearly, which is, I think, is a good assumption. I didn't tell you to expect otherwise. But now I have an area function with respect to time. So I can say pi times 4t squared, like that, right? 4 pi t squared. Yeah, that was one trap I was trying to set for you. So yeah, this whole thing needs to be squared. And the reason I did that is because I'm seeing a lot of this on quizzes and tests and from questions I get lately. Remember that when you're doing a substitution, you got to substitute the entire expression for a variable. And that usually means that there's some distributing going on. And then I had a question, why is it 4t? Why can we say it's 4t? Right, so like, let's do a table here. Yeah, t is time, so time since I threw this rock in the water. So let's make a table here, 0, 1, 2, 3. As soon as I throw the rock in the water, what's the radius of that wave? 0, right? After 1 second, what is it? And then 2. So maybe this is something I didn't tell you explicitly, but it's something you assumed. I'm saying it's a good assumption. Right. So based on this table I just drew, you should be able to recognize it as a linear equation. I can make an equation for it. That is indeed 4t. For any value of time, I can just multiply that value times 4, and I'll get that radius. We okay with that? All right, so now I had an area function that was a function of radius. Through this relationship here, I got an area function with respect to time. But now I want to find a rate involved here. So now what do I need to do to find the rate associated with I'm taking the derivative of at with respect to what variable? With respect to t. So I'm going to do that to both sides. So now I have dA dt is equal to what? 32 pi t. And we're very nearly done, but I want to make sure that people are okay with where that derivative is.
What is squared mean in the context?
But I'll write off somewhere else. I have a of t equals 16 pi t squared. Right, that's exactly it. So, and that's why I think it's a good idea to really spell out what all your variables are, especially early on. Yeah, the symbol A stands for the area of the wave, like encapsulated by the wave. And I say after 2 seconds because that area is always changing as time changes. Any other questions about where DADT came from or what anything on here represents? So are you okay with, so really where it came from is this formula that we've known for a while. The area of a circle is pi r squared. But in this specific case, we have a way to relate the size of the radius to the time that's gone on since I threw this rock in a lake. So another thing I should make sure of, are you okay with R of t equals 4t for this case? Okay. So all we did was substitute 4t in for this symbol R. We got what? Yep. Yep. Jordan? That's not an integral. I don't think we did any integration or trying to think what. I know that's what I assumed you meant, but I don't think. Oh, you know what? In a way, we did, and that wasn't intentional, but yeah, if I tell you that the rate of change is 4 constantly, then I can tell you that the function that might have come from was 4t. So yeah, I mean, we're not getting into integrals for quite a while, but yeah, if you can see how the derivative of this function gives you this other function, you can go the opposite way too. Okay, so we have dAdt equals 32 pi t. That's great for the general case, but I want it for a specific case. What's that specific instant where I care about this? So I'm going to evaluate this at 5 seconds, and I get 32 times pi times 5, which is 160 pi. So I'll just leave it as 160 pi. 160 pi. What's a good unit for this this quantity we just found? Meters squared per second. And does it make sense that as time goes on, that rate gets larger? So you have a circle that's growing. The radius grows constantly, but the area squares the radius to calculate it. So hopefully that makes sense that, you know, if I put in 10 for t, you would get something much larger, another larger rate. So did quite a lot here. Any questions about this example here? Okay. And really, I want to highlight this, like really what we're doing here is I'm giving you a look, but really we're just pulling together all the things we've done like in the last 3 or 4 sections. Basically the new wrinkle here is you have to come up with the function. But really the differentiation, the all the calculus stuff you have to do is stuff that we've been doing for a few days now. So this situation, I have a spherical balloon, air is being pumped into it. The volume increases at, and one thing that I'm not saying, but you can assume, if I'm saying the volume increases at a rate of 100 cubic centimeters per second, assume that this rate here is constant. If I'm giving you a rate as a constant, just assume that rate holds for any instant. So I'm not even going to get into the second sentence of this thing yet, because there's a lot of information we should probably look at from the first sentence there. So what's valuable from that first sentence? Air is pumped into a spherical balloon so that its volume increases at this rate. So it's a spherical shape, right? Spherical and volume. Can I come up with names for variables or quantities based on any of that? I think there's one variable we can pull out of this first sentence so far. Yeah, let's call it V volume. So V, that stands for volume of balloon. at t seconds. And what's a good unit for that? Not for volume. Yeah, cubic centimeters. What other quantity is implied in that? Time, yeah, so time, it's gonna be pretty common. Time elapsed. That's in seconds. Any other more information we can pull out of there? So that's probably gonna be something we need. So we have a formula for the volume of a sphere. What is that? So that formula, it is a formula, but let's think of it as a function. What's it a function of? Well, we don't have a formula this big, gives me V of t. So you're saying V is 100t? So that's true. In fact, why don't I put that over here? I'm going to say dV dt. Because really, if I have volume, I have time, I know those two things change together, then I can also represent that rate, that dV dt. That's going to be the increase of volume with respect to time. And I already gave you a unit for that. We'll call it cubic centimeters per second. And I also know, I'm going to rewrite this. I'll leave it up there, but I'll rewrite this like this. dV dt is equal to 100. Because, even the last thing we just did, we kind of rewrote the volume formula to be written in terms of time. I'm going to try to get away from that, and I'll show you how we can do that. So somebody mentioned the volume formula for a sphere. Anyone remember what that is? 4/3 pi r cubed. So this volume formula that you remember from geometry, this is a function in terms of what? It's a function in terms of radius, right? So the volume of a sphere is 4/3 pi r cubed. All right, so let's look at the second sentence now. I think we've kind of mined everything we can get out of the first one. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? So what new information did I just kind of breeze past there? Diameter. So yeah, I can think about diameter, but is there another quantity in there I can look at? Yeah, I mean, no need to do both. So I would like to do radius. Why am I preferring radius over diameter? Yeah, our function is written that way, and we could rewrite it for diameter, but no need to do that. So radius of balloon, that's in centimeters. What's the thing that I am trying to solve for in this question? I want how fast the area is growing. I want how fast the radius is growing, right? So I want how fast the radius of the balloon is increasing. Can I give that idea a name, a symbol? It's going to be a derivative, right? What in there tells you that's derivative? So I also heard, I'll write down drdt because I heard it. So we're trying to solve for drdt, but I want to back up to the last comment. What in that second sentence tells you that a derivative is the thing you're looking for? So the word increasing is a good tip. Quantity. In this case, it's drdt because how fast is the radius increasing? So I'm going to take over here because one thing I want to get in the habit of doing is, dealing with these derivatives, without substituting in some function for time. So I want dr dt. So what I'm going to do is this. I'm going to differentiate both sides of this equation with respect to time. The left-hand side, what's the derivative of volume with respect to time? I can just call that dv dt by definition. But then the other part of this is I need to rewrite this so I have room to. So I'm trying to differentiate a function with respect to time, even though time is not the variable there, right? So this, maybe you realize it or maybe you don't, but this is going to be an instance of chain rule. And to point out why, what's going on here is this. I have time, which goes through some process to be translated into a radius. And then radius gets put through this thing, 4/3 pi radius cubed. That gives me the volume. So you can look at this as there being, I have a function nested inside another function. I have a composite function. I should stop there. Okay with the fact that I'm calling this a composite function. If we're okay with that, then we can just differentiate that the way we always do, or the way, not always, the way we've done this week. I can take the derivative of this outside function with respect to r, and that'll give me 4 pi r squared. So I guess one thing I should say is this. The derivative of volume with respect to time is going to be equal to this. The derivative of volume with respect to r times the derivative of radius with respect to time. And I don't think I've represented the chain rule like this before, but this is another way to think about the chain rule. I'm taking the derivative of the outermost function with respect to whatever that intermediate variable is. And then I'm taking the derivative of that inner function with respect to the independent variable, in this case, time. So this 4 pi r squared, that is dv dr. And then dr dt is that other rate that results from the chain rule. So we've done quite a lot. We're very nearly done. From here, it's just a matter of substituting, but I want to make sure we're on board with what happened here. Any questions about how we came up with this dv dt equation? All right, so we've identified what we want to solve for. Do I know what the other quantities are? So I want dr dt, so I better know everything else. Do I know dv dt? It's a constant 100, right? So yeah, dv dt, and if you're ever unsure about whether or not you have something, just think about, okay, dv dt. Let's translate that to English. What does that mean? What does dv dt mean? So that's true, but like, what does that mean in terms of like this situation? All right, it's how fast the volume of whatever object, in this case the balloon, how fast that volume is changing, right? So in this case, that's 100 cubic centimeters per second. So I know that one. Times 4 times pi, do I know the radius? Oh, I didn't catch you. It's 25 squared, and then dr dt. So from there, it's just a matter of calculating that, and I will let somebody else do that while I take a question. You have questions, Matthew? Like 25 over pi or something like that? believe this is the answer. 25 squared is 625 times 4 is 2,500. Nope. Feel better about that. Sebastian? Not very carefully. So let me write down my process. So 100 equals 4 times pi times 625 times, I'll just call this x for now, this thing I'm solving for. 100 equals 2,500 pi x. X equals 100 over 2,500 pi. Okay, I feel better about it now. But I actually read it out. Jordan?
Where the PR, like, we were trying to find
Sure, and I think I'll highlight this block diagram at the top. This is pretty common, but in all these situations, kind of the variable that governs everything will change. In this case, as time goes on, radius becomes correct. But as the radius so I have So I'll call this function r of t. I'll call this function v of r. So then what you really have then is v is a function of r, which is a function of t. Which is, and I think a lot of the things we looked at on Monday, like how do we find the derivative of a function where that looks like f of g of x? And the way you do that is take the derivative of f with respect to whatever's inside of it, so whatever g of x is, then take the derivative of g with respect to x, then multiply those two components together. So what we have here is basically the word problem version of that. I didn't give you the functions, we had to build them from the thing I described. So taking the derivative of the outer function here, I have the derivative of volume with respect to radius, which that comes from this guy here. Following the power rule on 4/3 pi r cubed, that derivative becomes 4 pi r squared. And then dr dt, we don't know enough about the function r of t to be more specific there. Very close. We're actually doing this. You may have meant this, but it's actually the derivative of f of g of x times g prime of x. I believe you said f prime of x times g prime of x, which is not quite. So when you're doing chain rule, whenever you're dealing with that outer function, you have to respect what the input to that function is, which won't be x. Correct. Which is what we did here. The derivative of 4/3 pi r cubed is 4 pi, not t squared, but r squared. Because that inner function, the input to it was, oh, sorry, the input to the outer function was r. Yeah. This thing right here. So the first thing I have to do Only one layer inward. Derivative of that function R. Yeah, a lot of things going on here. We got plenty of time to talk about all of them, so please ask me questions. Anything else before we go on to another one? Okay. Vertical wall. One thing we haven't done, which might be a good idea to do, is this. Actually, draw the thing we're talking about. The wall and a floor. The ladder. Do I know anything about this ladder? 10 feet long. So how can I mark that 10 feet on this drawing, this crude drawing here? Yeah, the hypotenuse is going to be 10 feet, right? Is that constant? How about this horizontal and vertical leg? Think that'll be constant? No. Why not? Right. So the ladder is going to slide down the wall and across the floor. So the length of the ladder is not going to change, but the height on the wall and the length along the floor, those two things are going to vary. So I got a ladder 10 feet long against a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 1 foot per second. So in terms of variables, what should we do here? What variables are there? Wall and the floor, what do you want to call them? W and F sound good? If I can write them. Nice, fine. W and F. Okay, so now that we've written them, let's talk about them. W is the height of ladder up the wall. That's in feet. F is the length of ladder along the floor. Also feet. What other variable do you suspect is going to make an appearance? Always time, right? No, I shouldn't say always, but what's a dead giveaway? Definitely. Deal with that. Okay, so I got these three variables. What else is important that we haven't written down? The rate, what? Okay, what do you want to call that rate? What does dFdt equal? Do you agree with that? Okay. So yeah, it says the bottom of the ladder, sorry, no. The bottom of the ladder slides away from the wall at a rate of 1 foot per second. We assume that's constant. So we have dFdt equals 1 foot per second. Do we know what we're trying to solve for? Okay. I think we're given that. I think I want to find dw dt. And I think what you just described would be W itself. So, and just another cautionary, I mean, this is one thing that's really hard to wrestle with is when am I dealing with so I know df/dt. I want dw/dt. I think I have a pretty good idea on how these things are all related. What am I missing here? Do we know, Sebastian? Yeah. So I'll turn our question to how it's worded. The bottom of the ladder slides away from the wall at a rate of 1 foot per second. So the bottom of the ladder is sliding away from the wall. So, and that's why, oh, I'm sorry, did you have more? I'm sorry. Oh yeah, so yeah, so a couple caveats to provide you from that. It's probably a good idea to read these things through a couple of times and just to kind of take notes on what you think is important each time. Also, it's a really good idea to draw a picture if you can, define the variables as explicitly as you need to. And I'll tell you just, I mean, I've been teaching or tutoring calculus in some form for 15, 20 years. If I was doing this without any of you, I would still do this kind of the same way. Like I'm not really like throwing things on you because I'm teaching it to you. This is kind of, it's just good to be organized with this stuff. There's a lot of moving parts to keep track of. All right, so I have df/dt. I want dw/dt. I think the next big thing I need here is I need some kind of relationship that joins all the things together that I know about and want to solve for. Okay. So I heard Pythagorean theorem. I think I want f and w to be related somehow. I think Pythagorean theorem is a good way to go. So f squared plus w squared equals 100 is a good equation. All right, so there's my equation. What do I need to do to it? Sorry, what? Think about what we did last time. Do we need to isolate variables? So we could isolate a variable. We actually don't need to. So I'll say I'm not going to isolate w, but we absolutely could, and this will all work fine. But we could just implicitly differentiate everything, you know, just as it's written. Right-hand side becomes what? Zero. The left-hand side. So I want, remember, I am differentiating both left and right with respect to time. What's the left-hand side become? Heard. So 2f times df dt. I don't know why I decided to do f like that this time. Plus. All right. So let's keep an eye out here. I want to solve for dw dt, which means I better know everything else. We already wrote down df dt. I know it. So I know f and w. Or a no and then a yes. Now, which one are we told? We're told when the bottom of the ladder is 6 feet from the wall. So we're told F, right? We're not told that done. So we can find it. I mean, we know this relationship. F squared plus W squared equals 10 squared. Since we know that F is 8, sorry, F is 6, I just gave it away. 6 squared plus W squared equals 10 squared. Hopefully you see that means W is 8. which means I have now all the pieces I need. So 2 times F, which is 6 feet, dF dt, which is 1 foot per second, plus 2 times W, which is 8. We get 12 plus 16 dW dt equals 0. Ends up being dW dt equals -3/4. I got a negative number for dW dt. Does that make sense? Why does that make sense? It's decreasing, right? So yeah, the rate of change, yeah, it's representing a drop. W is decreasing as time goes on. Any questions here? So I don't think I've opened the web work for this one. I will open it. I'm not going to assign a due date. I want to do at least 2 more examples of this because I feel like it deserves it. A lot of stuff going on there, and we're pulling together like pretty much everything else in this chapter. So I think it deserves the extra practice. Like I said, sometime today I'm going to post a quiz. After I'm going to go ahead and stop here. But like I said, I got tests for you, so stick around.